Welcome to this next lecture in the optics module, lecture 9, microscopes and telescopes. In the last lecture, we discussed about the basic principle of a simple microscope or a magnifying glass. So, we saw that the magnification is given by an expression of the form, the magnification is given by m is equal to magnification m is equal to d by f. F is the focal length of the lens. So, focal length of the lens, that is the simple microscope or the magnifying glass, and d is the least distance for clear vision, which is approximately equal to, which is assumed as 25 centimeters. We have already discussed that d depends on the person to person, it varies from person to person, but we assume that d is equal to 25 centimeters. So, this is the magnification, and we have also seen that there is a certain limitation in practice, because f cannot take very small values and d is fixed, and therefore, there is a limitation on the magnification. In practice, there are several samples, many samples which require very large magnification to be seen, like biological samples like blood cells or bacteria. If one has to visualize these, the magnification required is very high, and a simple microscope or a magnifying glass will not do. So, what is done is we use what is called a compound microscope. A second additional lens, there could be more lenses, but in its simplest form, a compound microscope comprises of two lenses, one additional lens which is compounding the effect of the first lens to give you a higher magnification, hence the name compound microscope. So, we will start first with the compound microscope and then we will come to the telescope. The compound microscope. So, first I am showing here a simple diagram of a compound microscope, which comprises of two lenses. One lens here, it is called the objective lens, because the object is placed close to this lens. This is a metallic tube. There are two cylindrical metallic tubes which are coaxially located, and there is a knob, adjustment knob. I will show you a typical instrument. There is a knob by which you can adjust the separation here, or you can move the objective closer to the object or away from the object, and this is the eye. So, the separation between the two lenses can be changed to get a clear image by using the adjustment knob. So, a compound microscope, we will see the ray diagram and how the magnification takes place, etc., but in its simplest form it comprises of an objective lens here and an eyepiece here, and this is the eye from where you see. So, let me first show you the instrument, how the instrument looks like. So, let me show you a laboratory microscope, a compound microscope which is used in the laboratory. So, here, so let me show you a compound microscope. I am showing it in a slightly in an angular fashion. So, here is the microscope. So, we have the eyepiece which is here and the objective lens which is here. So, I can show you like this, for example. So, you can see that the eyepiece, this is the objective is placed in front of this lens, objective lens, and the eyepiece is closer to eye. In other words, we see from here that we see from here through the eyepiece. And what I would also like you to note, so again let me rotate this and show you this fashion. So, here is the objective, and at this end we have the eyepiece. You can see the size of the lenses, the objective lens and the eyepiece here. The lens, we can also see the eyepiece here. So, from front side you can see the eyepiece. It is a very small lens, and if you keep the eye, you will cover, your eye will cover this lens. It is just to note that the eyepiece lens is almost of the same size as that of your eye lens. So, let me again keep it like this and show you that the knob, adjustment knob which I had shown. So, let me show from the side here. So, you can see that if the object is kept here, then I can increase or decrease the separation between the object and the objective here. So, the object is placed here, you can increase or decrease, so that you get a clear vision when you see from the eyepiece which is here. Also note that the eyepiece, there are in some microscope there are other adjustments, but this itself can be varied. You can see that the eyepiece lens here, this can be pulled back, so that the separation between the objective and the eyepiece. So, let me show you here. So, the eyepiece is here, objective is here, the separation can be increased or decreased to get a clear vision, but normally that is not required, and once it is set, you need to adjust only the position slightly between the object and the objective here to get a clear image. There are other screws which are provided here. So, this is not a microscope which you see in a biology laboratory where the biological samples are seen. This is in fact called a travelling microscope, because it can also travel in different directions. So, it can move laterally, it can move horizontally. So, you can, there are additional screws provided for this to move in this direction and that direction, both the directions it can move, hence it is called a travelling microscope, widely used in the physics laboratory. But basically this is the microscope tube which I had shown earlier, which has an eyepiece and an objective. In a specialized microscope, you may have many more objectives here. You can switch from one objective lens to another objective lens with a different focal length to get a higher magnification. So, this is the a laboratory compound microscope. So, let me come back to the discussion on the microscope. So, let us come back here. So, here it is. So, the original diagram which I had shown, that it is a tube, one tube into other tube, and the adjustment knob here, the adjustment knob by which we can move the objective lens, and here is the eye which you for observing the image. The object is placed in front of the object lens, and this is called eyepiece because it is closer to the eye which observes the image. Now, we will see the ray diagram and the layout of the compound microscope to understand the picture more clearly, how a object is magnified and how the image is formed. These are the two lenses which I showed you earlier, the objective and the eyepiece. So, the object is a very small object because we are discussing about a microscope. A microscope is used to observe very small objects. So, there is a small object here in front of the objective. FO is the focus of this objective, and the small FO here, the small FO is the focal length. So, focal length of this lens, and the object is placed a little bit away from the focal length, and we know that this forms an image here. Using the lens equation, you can find out the position of the image. So, this is a inverted real image formed due to the first lens, which is the objective in our case. So, the image is formed here. The second lens gives a magnified virtual image, provided this image falls within the focal length of the second length. FE here is the focus point of the eyepiece, FE is the focus of the eyepiece, FO is the focus of the objective, and small FE here is the focal length of the eyepiece. So, if the position of the object, so this we can adjust by separate by changing the separation between the object and the lens. That is why I showed you there is a knob which changes the separation between the object and the objective. So, by changing this we can make the real image to form very close to the focus of the eyepiece, but within the focal length, that is slightly less than the focal length here. So, that we get a magnified virtual image. The ray diagram drawing, we can see here that the ray which passes through the middle of the lens, midpoint of the lens, passes undeviated. There are other rays also which can be shown, but I have shown only 2 rays to avoid complications, and the ray which passes through the focus here, any ray coming from the focus will be rendered parallel. So, this is coming parallel, and the parallel ray will get again pass through the focus F e on the other side, that is the second focus of the eyepiece, and that is how this is going here, and this ray bends towards this, and if you project it back, then it appears, these rays appear to come from a virtual object, a position which is positioned far away, and this is a magnified image of the object. Note that the distance L, which is the separation between the two, that is the focal length here, the focus, and the focus of the eyepiece, the separation between the focal point of the objective, that is the second focus of the objective, and the first focus of the eyepiece is called L, is designated L, and it is called the tube length. It is not really the physical tube length, but it is called as the tube length because it is very close to the tube length, actual tube length. That is because FO and FE here are much smaller compared to the actual tube length of the microscope. The tube length of the microscope. So, if you see the original diagram, so we may say that this is the tube length, almost the separation as the tube. This is the tube and this is the length of the tube, but it is not exactly the tube length, because the focus, typically the focal length of this objective is 1 centimeter or less, and typically this is also of the order of 1 centimeter or 1.5 centimeter, whereas the tube itself is typically 15 to 20 centimeter in length. The separation between them, this L is typically 15 to 20 centimeter, whereas these are approximately 1 centimeter, because we use a objective and an eyepiece, eye lens here, eyepiece, which have small focal lengths. So, L is the tube length. So, this ray diagram clearly illustrates how a small object, first a real inverted image is formed by the objective in a position which is very close to the focus of the eyepiece, but inside here, that is closer to the eyepiece, and therefore, a position, the object position is such that we get a virtual image, an enlarged, a magnified virtual image. This is just like this part is the same as that in a simple microscope or magnifying glass, which we have discussed in the last class. Now, we have added only one more lens here, which gives a first magnification here and then a second magnification here. Therefore, we have a magnification which is almost doubled. This can be not really doubled, it could be many more times. So, this could be seen as an image formed due to the first lens followed by image formed due to the second lens. So, here I have pre-drawn another diagram just to make it clear again that we have this first length. So, I am first showing the first lens here forming a real image. So, first lens. So, I had shown in the previous diagram only these two rays, but here I have also showed a parallel ray passing through the focus here and reaching the same point, of course, and this is the object and this is the real image formed by the objective. So, FO, FO and L. Now, in the same position I am showing now the eyepiece. how it forms a virtual image, a magnified virtual image. This is working like a magnifying glass, and this is like an imaging lens. Now, you superpose this over the other, and what you have is the compound microscope. The magnification here is m is equal to h dash by h, which is a dash b dash divided by a b, and we can show that this is nothing but h dash by h is equal to f 2 b dash here divided by f divided by p times f 2 here, because these two are similar triangles, triangle f 2 b dash a dash and triangle m p f 2 are similar triangles, and therefore, we have h dash by h, that is this by this, is equal to this distance divided by this distance. This distance is the focal length f o and f 2 b dash, but f 2 b dash is very close to L, because we have shown in the, if we see the earlier diagram, we can clearly see that it is this distance which is almost equal to the separation L, and therefore, f 2 b dash which is close to L, and therefore, we have magnification is equal to tube length L divided by f o. So, the first magnification. Now, the second magnification we have already derived in detail in the last class, that the angular magnification that you get is d by f e, where f e is the focal length of the eyepiece, and therefore, the net magnification. So, the net magnification m, the net magnification m is equal to the first linear magnification multiplied by m theta. So, this is the overall magnification is equal to m linear and m theta, which is equal to, we have L divided by f o into multiplied by d by f e. So, m, the total magnification m is equal to L into d divided by f o into f e. We can see that the magnification will be larger if f o and f e are smaller. That is why one chooses the objective of a small focal length and eyepiece also of a small focal length. Similarly, L, if the tube length is large, then the magnification can be large. So, d is of course fixed, d is the distance for least distance for clear vision, which is taken as 25 centimeter. We have already discussed in the last class that d actually varies from person to person. However, for on an average it is approximately 25 centimeter, and we assume d as 25 centimeter. L is the tube length. So, if we take a typical example, if we take an example just to get an idea what kind of magnification we have. In a simple magnifying glass, we had a magnification m which is equal to d by f e only, this part only, d by f e, which was approximately 5 to 8 or maybe 10 that one can get. But now, let us see in a typical example, if you have an objective f o of focal length is equal to 1 centimeter and a 1 centimeter or 1.5 centimeter, let me take 1.5 centimeter, and f e the eyepiece of focal length 2 centimeter. You could also take smaller values, and d is of course, and a tube length L is typically approximately 15 centimeters, and d is equal to of course 25 centimeter. We can see that the magnification m is equal to L into d, that is 25 divided by 1.5 into 2, all in centimeters, and that is 1.5 into 2 is 3, goes 5 times. So, this is 125, all centimeters cancel, this is dimensionless, and the magnification is 125. Whereas, earlier we got a magnification of about 5 to 10 with a single magnifying glass. Now, we have a magnification which is 125. So, this clearly illustrates that by using an additional lens to enhance or to compound the effect of a single lens, we can get much larger magnifications. In fact, one can have focal lengths FO objective focal lengths which are a few millimeters, 1 millimeter, 2 millimeter, in which case you can see that the magnification will go further higher and you can easily get magnification of the order of 1000. So, this is a compound microscope. Now, let us move to there are many more problems which one can work out, but let us now move to the telescope. So, what is the telescope? So, telescope, recall that telescope is an instrument to measure, to observe an object at a large distance, tele, that is at a far away distance. When you have an object which is at a far distance, so you are observing from here. So, this is the human eye or eye lens. So, let me show this as the eye lens, and this is the retina we have discussed in the last class. If you have a big object, but which subtends an angle, a certain angle theta here or alpha at a certain distance which is u here, then the angle alpha subtended at the eye is alpha. The same object, if it moves away, let us say it moves to same height, is the same object, then this will subtend an angle which is smaller than alpha. And if the object is at a very large distance, then the angle subtended is very small. In other words, if the object is almost like infinity, for example, let me take some practical numbers. If I take some practical numbers, for example, you take, let us take moon, we take moon. Moon has a mean diameter, average diameter size diameter of approximately 3.48 into 10 to the power of 3 kilometers, and the distance from earth to moon, the distance is approximately 3.84 into 10 to the power of 5 kilometers, the earth moon distance. Now, the size here, the diameter. So, we have a situation. So, here is the moon, which is, so here is the earth and an observer is here. So, what angle would this subtend here at the observer or into the observer's eye? This is the diameter and this is the distance, this is the distance. So, this theta, how much will this be theta? Theta is equal to, obviously this arc length is equal to r theta, or theta is equal to the separation. So, theta is equal to 3.48 into 10 to the power of 3 kilometers divided by 3.84 into 10 to the power of 5 kilometers. So, this is less than, nearly equal to, less than, if I say that this is almost 1, it could be, it may be about 0.8. So, approximately 0.8 into 10 power minus 2 radians, 10 power minus 2 radians, approximately 10 power minus 2 radians. That is the kind of angle that you have here subtended on the eye, onto the eye of an observer. Similarly, if you take the distance of sun, so sun, if we take sun diameter, average diameter of sun is approximately 14 into 10 to the power of 5 kilometers. This is the diameter of sun, and the distance earth to sun, is approximately 1.5 into 10 to the power of 8 kilometers, or 15 into 10 power 7 kilometers. As before, the angle subtended theta is equal to 14 by 15 into 10 power minus 2, which is approximately 1 radian, 1 into 10 power minus 2 radians, approximately, almost same. Obviously, we can see it is very clear to us that our eye can clearly see the moon, clearly see the sun, although they are at a far away distance, because the angle subtended is of the order of 10 power minus 2 radian. The angle resolution, the angular resolution which the human eye has is of the order of approximately, it varies again from person to person, of the order of 10 to the power of minus 4 radians. For example, if moon were to be 1/10 of the size, so moon were to be 1/10 of the size diameter, even then we could have seen the moon, because we can see the moon clearly, quite big and clear. Now, if the size reduces to 1/10, I am sure we will still be able to see. If it reduces to 1/10, this theta will come down to 10 power minus 3. So, minus 3 radians. The human eye can have an angular resolution of the order of 10 power minus 4 radians. Now, coming back to our discussion on telescope, the important point which I wanted to show, wanted to illustrate by these numbers is that the angle theta is extremely small, or the rays travel very close to the axis, parallel to the axis. The rays which come from the object are almost parallel. With this, if I keep back the telescope, so before we discuss the telescope, let me show you a laboratory telescope here. So, back again. So, here is a laboratory telescope which I have just picked up from the physics laboratory. So, here is the telescope. So, we can see this has an object lens here. So, there is an object lens and an eyepiece here, and as before you can see there is a knob. So, we can move the knob and change the separation, because this is clamped, the tube which holds the object lens or objective is clamped, and therefore, we can change the separation. We can change the separation between the object lens and the eyepiece by moving this knob. So, this is important. We will see why that is important, because by changing this we can adjust the separation such that we get a clear image of a distant object. So, we can see from the front here. So, this is the object lens here. So, this is the object lens, and on the other side. So, if we see like this, so this is the eyepiece, and as before you can see that the lens is quite small, it is almost the same size as our eye. So, here is the eyepiece, and so here is a typical telescope. So, what is the difference that we see? I showed you just now an objective, a microscope, and now a telescope. The basic difference we can see is, we can see externally, just by outside we could see, is that there was an objective which was small, a small objective lens. Now, you have a slightly bigger objective lens, and the eyepiece looks of course almost similar in that case, but clearly the object lens which I showed you on the microscope was of smaller diameter. Otherwise, they look similar. Now, let us discuss the ray diagram and try to understand more about the telescope. So, come back to the discussion on the telescope. So, object lens, you can clearly see, now I have showed a bigger lens here, the objective, and eyepiece is here of a small focal length, whereas the objective is of a longer focal length and also a larger diameter. Parallel rays are coming from the object. So, there are rays coming from the object. There are also rays which are coming here, but I have not shown them, because just to avoid confusion, I have chosen two rays, because we can locate the position of the image by just having two rays. One ray passing through the midpoint of the lens, which goes undeviated here, and the second ray which has passed, which has come from the focal length. You can see the focus is here. So, the focus is somewhere here behind, and this has come from the focus, and therefore, this must be rendered parallel after passing through the lens. So, these two intersect here to where a real image, a real inverted image is formed. Now, the distance is very large, therefore, rays are almost parallel rays, and therefore, the image will be formed on the focal plane, at the focus on the focal plane. Therefore, the first thing that we see is, and this image helps, or this image acts as an object to get a magnified virtual image of the same by the eyepiece. This functions as before, the eyepiece functions as before, that is, it gives us a magnified image, a virtual image of the object which is placed close to the focus of the eye. In this case, since the actual real image, inverted image is also formed at the focus of this lens, that is the object lens, we have FO and FE almost coinciding at the same position. So, that is why FE. So, this is the point where FE and FO are coinciding, whereas focal length FO is larger, FE is small. So, that we get a magnified virtual image. The magnification is, this would have been the angle subtended at the eye if the eye were to be here without the telescope. So, if I were to be here, if we were to observe the object directly, alpha would have been the angle subtended. But because of this arrangement, now the angle subtended at the eye is beta. We can see here beta is the angle subtended at the eye, and therefore, the angular magnification is beta divided by alpha. That is the magnification, beta divided by alpha. Beta is the angle because of the telescope. And what is beta? If you look at this diagram, so beta here is h dash divided by f e. So, we can see that beta nearly equal to tan beta, we are talking of extremely small angles. That is why I put some numbers and showed you that alpha here is of the order of milliradians or 10 power minus 2 radians, and therefore, tan alpha is equal to alpha, tan beta equal to beta holds good, and therefore, beta is equal to h dash here divided by f e, the focal length of the eyepiece, whereas alpha here is equal to h dash divided by the focal length here. So, that is f o, h dash divided by f o. Following convention, because this is an inverted image of a erect object very far away, it is minus h dash by f o we have used, and therefore, whereas this we have not used a minus h dash, because this is whatever be the object itself is like this, and therefore, the image is also in the same direction, there is no change of direction. Here we can see that the object was erect like this, that is arrow pointing upwards, the arrow was pointing upwards far away, and the arrow is now pointing downwards. So, there is a inverted image which is formed, whereas here it is in the same direction. Therefore, h dash by f e by this, which gives us minus f o by f e. Note that the angular magnification is equal to, the magnitude is f o by f e. Therefore, larger the focal length, larger will be the angular magnification, and smaller the focal length of the eyepiece, larger will be the magnification. But of course, there is a limit for this smaller value, because we have already discussed why we cannot go below a certain value, but f o can be made large if you have a large focal length. Now, magnification, so exactly like this one can analyze, one can simply take the first lens and look at this image formation, then one can take the second lens, and the compound effect is what the telescope forms. Compare the telescope and the microscope. In the case of the microscope, we had a f e which was small, f o, the object focal length was small, and f e was here, and the separation between f o and f e. So, let me keep the diagram just to recall. So, the separation, so here is the ray diagram of the compound microscope just to recall. So, this is FO and this is FE. The points are well separated and the separation is called the tube length, whereas in the case of a telescope FO and FE coincide, first difference between the two, and the lens here has a large focal length if you want to get a larger magnification. Magnification is just one of the issues. In the case of a telescope, magnification is just one of the issues. There are several other important issues. So, a telescope which is used to observe a distant object which appears very small. So, magnification is required. So, magnification is an issue. Magnification. However, since the object is at a very far away distance which subtends a very small angle at the eye, to observe an object which is very far away, we should also have sufficient amount of light entering from the object. That is, if I can draw here. So, there is an object here like sun. So, it is giving out radiation in all directions, that is into 4 pi steradians here, or the area, the surface area of 4 pi r square all around, and the radiation which enters a small cone which is formed on the observer here is very small. The fractional light entering this cone of angle alpha, which is of the order of 10 power minus 2 radian, is very small. A very small fraction of it enters this eye. Therefore, when the unless we have a large aperture here, larger the aperture, that is, if I have a larger lens here, then instead of a smaller lens, then the amount of light which enters the eye would be much more compared to the amount of light which would enter if I had a smaller lens. Let me draw a smaller lens here. So, I have a small lens, same parallel beams, but the amount of light which enters this small lens is much smaller compared to the amount of light which enters here. Therefore, if the light is insufficient, it will be so weak that it would be difficult to observe the object even though it is magnified. The object may have been sufficiently magnified, but the amount of light which enters through the objective lens is so small that it would be very weak or maybe indistinguishable from the background. And therefore, magnification is one issue, but the second important issue is the light gathering power. Light gathering power or capacity, light gathering capacity. So, this will depend on the size or the diameter of the objective, diameter of the objective. Larger the diameter, larger will be the amount of light which enters the objective in forming the image. Now, larger diameter of the objective makes it very heavy because the lens is made of glass, and therefore, this becomes very heavy. This implies it becomes very heavy, and fabricating, and so fabrication of such lens, so difficult, fabrication becomes difficult. So, I am just highlighting the points, practical aspects, fabrication becomes difficult. people have fabricated lenses of 1 meter diameter, but it is extremely difficult to fabricate such large lenses. This is very heavy. So, fabrication and supporting also be supporting this in the tube. So, in the tube has to hold the lens. So, supporting the lens in the tube, in the telescope tube, becomes difficult. So, what is the solution? So, it was proposed that instead of using a lens, one may use a mirror, a concave mirror. So, going over from lens to mirror. So, how is that possible? So, the same configuration. So, let me draw this diagram here. So, we have parallel light coming from a distant object like this. We have a large concave mirror, So, light is, I am not showing on the other side, which then focuses if the focus is here, let us say the focal point is here, then the rays will form an inverted image at the focus. So, at the focus an inverted image will be formed. So, let me link just to make it clear. So, these are the rays which form an inverted image, just as in the case of the lens now, but in front of the mirror, in front of this mirror. So, we have achieved a small inverted image of the distant object at the focus or on the focal plane of this concave mirror. But because it is a mirror, one can fabricate such a mirror by having several pieces making into one mirror. Huge mirrors of the order of diameter of the order of 5 meter to 10 meter have been fabricated. 10 meter dia of the mirrors 5 meter to 10 meter have been fabricated. You can have different segments, pieces of the mirror which can be put together. And second, holding, this can be held with a huge a metallic steel beam or something like this. I am just showing some typical way it could be held. So, this is a base and a metal support which is holding the mirror, because now you can hold it everywhere. If you had a lens, if we have a lens, and because the image is formed in the transmission, you have to hold it only at the edges, otherwise you will obstruct the lens. So, holding only at the edges of a huge and heavy lens is extremely difficult. But here is a mirror, a concave mirror, which can be held by providing steel or metallic support all over the mirror and mounting over huge supporting structures. But the difficulty is in this case is that in this case the image was formed somewhere on the other side here. So, the image was formed here, and therefore, you could have kept a eyepiece here to get the magnified image, virtual image of this object. But in this case, this has to be observed. So, the observer has to sit here. So, we have to keep an eyepiece here such that it is at but within the focal length of this, so that a magnified image can be seen, a formation of a magnified image can be obtained here. The problem is the lens has and the observer I am showing just his eye. So, the observer's eye here. So, this is the eye of the observer has to be on the same path, because the parallel rays are coming from everywhere from a far away distance. So, these people are also the person, observer and the lens are blocking the part of the light which is entering, which is incident on the mirror. However, it is possible to have some other configurations wherein the image can be formed in the forward direction. For example, one of the configurations which is used. So, before I proceed, so this kind of a telescope is called reflecting telescope, reflecting telescope. So, a reflecting telescope is one where the objective is a concave mirror, a reflecting mirror, instead of the lens which we have used as an objective earlier. Whereas, the telescope that which we had seen earlier, where lens is used as the objective, here is called a refracting telescope. So, a refracting telescope. So, reflective. So, telescopes. So, telescope. The principle is the same. So, telescope can be reflecting or refracting. So, this is refracting telescope, refracting type, which uses a lens, an objective which is a biconvex lens, whereas it could be reflective type, where the first image, the real inverted image is formed by a mirror, using a mirror. So, this using a mirror, whereas usually a concave mirror, and this uses a lens as the objective, lens for objective. This is the primary difference between a reflective type of telescope and a refracting type of telescope. So, this is the objective, this forms the objective. The second part of the magnification process is identical, that is, you have a lens. So, whether it is a reflecting type, a refracting type, where you have the object which is then viewed, the virtual image is formed on the eyepiece here, whereas in the case of a reflecting type of telescope, the real image is then viewed through an eyepiece to get a virtual image, a magnified virtual image. So, these are the two types of telescopes, refracting type and reflective type of telescope. Finally, we have one more type of telescope which is called terrestrial telescope, terrestrial telescope. I will briefly describe this terrestrial telescope. The telescope that we had, so terrestrial telescope and astronomical telescope. If you see in some of the books, it is written that astronomical telescope, astronomical. Astronomical telescope. Astronomical telescope is a telescope used to observe celestial bodies, such as sun, moon, stars. Here, since they are usually in the form of spherically symmetric, it does not matter whether you see the object inverted, or it will always, for example, if you see sun like this or inverted, it will look identical, and therefore, it does not matter even if you see the image as an inverted image. Therefore, in astronomical telescope, which is the telescope, which is the normal telescope which I have just showed. So, the normal telescope, where you see an inverted magnified image, here of the body of the object which is far away. Arrow we have used only for our convenience, but a celestial body like sun or moon or planets, they do not have, they are spherically symmetric, and therefore, it does not matter whether it is inverted or not. However, a terrestrial telescope which is used to observe terrains or distant terrains or landscapes or objects which are on the earth, but very far off, which you want to see clearly, for example, using binoculars, then you would not like to see an inverted image, you would like to see an erect image, and then we use what is called as a terrestrial telescope. The principle is the same, except that now we have, so we had an object lens here. So, I am drawing it quickly, which formed an image here, a small inverted image of a distant object. So, there is a distant object which formed a small image here, inverted image. Now, we use one more lens to invert this image. So, this is placed at, so this separation here. So, if we place a lens inside the telescope such that the image is formed at a distance 2f from this lens, 2f, f is the focal length of this lens here, the in between length at a distance 2f, then you will see an inverted image of this, which means erect image of the distant object, erect image at a distance 2f. So, 2f is the object distance here and 2f is the image distance, and magnification is just 1, because magnification is V by U. So, it is 2f by 2f, but magnification is -1, which means if the original object is like this, we will get an inverted object image, which is the erect image of the distant object. Now, you use the eyepiece. So, we use the eyepiece here. So, this is the eyepiece such that it is at the focus of this to get a virtual image. So, we have a virtual image formed. I am drawing right in front without any scale. So, we see that a virtual image is formed at a distance. So, I have simply, these are the actual ray paths, but they appear to come from a point here. So, this is the original eyepiece. So, this is eyepiece, this is the objective as before. So, only thing that we have added is a lens here, such that the original image is formed. So, this distance now, so we have this distance. If you recall, the image is formed at FO and this is FE, this is FE. In an astronomical telescope, the total separation, the separation between the two lenses is L is equal to, let me call it as L is equal to FO plus FE. But in the case of a terrestrial telescope, we have L. So, this is astronomical, this is length of the terrestrial telescope is FO plus 2f plus 2f. So, 4f plus f. This is the primary difference between an astronomical telescope and a terrestrial telescope. So, this, let me write the title. What I have discussed is a terrestrial telescope. Terrestrial telescope. terrestrial telescope. So, just to wind up, therefore, we have discussed refracting type of telescope, reflective type of telescope, astronomical telescope and terrestrial telescope. So, in the case of an astronomical telescope, the separation between the distance between the objective and the eyepiece is FO plus FE, whereas in the case of a terrestrial telescope, we have to use an additional lens to re-invert the image to get a erect image of the object. So, that there is an additional distance of 4 f, where f is the focal length of the lens which is introduced in between.